There we go. No idea what I did to I could do that. All right, so you want to describe to someone else the direction of motion of the wheel here. How would you do that? I would contend it's going counterclockwise.
Yeah, normally it's 0, 90, yeah, we go control.
You're backing him up, say it's clockwise?
Well, it's
From our point of view,
I think
clockwise.
this is negative, this is going negative.
So, Kyle, what'd you say?
From our reference.
Yeah, that gets really wordy though of, what's the direction that the wheel is spinning? Well, if you're standing in the main part of the room and looking towards the front, it's traveling clockwise. Surely there's an easier way of doing it. And there is. So the math people got together, at least I blame the math people, and they came up with, of course, a right-hand rule. So the wheel is spinning around like this. And so you basically treat your thumb, assuming that's, right angle-ish, as the axle, which means since the axle is running towards the back of the room, front of the room, which means my thumb's either pointing towards the back of the room, or the front of the room, or the back of the room, one way or the other. You want your fingers to curl in the direction that the wheel is spinning. So if it's spinning like that, that means the thumb has to point towards the front of the room, so that my fingers point in the direction that it's rotating. So the direction of the angular velocity is that way. That is the convention they have set up. So if I close that door, the direction of the angular velocity, correct, is up. Which means that the angular acceleration, since it starts at rest, and then the angular velocity is up, that means the angular acceleration has to be up. Which means the torque I apply has to be up. Now, when I was first going through this as a student, that confused me, because I kept trying to picture what physically is going up. When I push that door closed, what's going up? Nothing. Nothing physically is going up. It is the convention that has been set up in order to be able to communicate more easily, and the math also works. So this one, if we set up our coordinate system, I, J, K, the direction of the angular velocity is negative K, because it's spinning around like that. Questions there?
But wouldn't it depend like how you're facing it? Because like if I was doing that, it'd be facing this way.
Except you're using your left hand.
Okay.
Yeah, it is the right hand rule, regardless of, it's not the dominant hand rule. Yeah, so that way it works for everybody. So if we weren't in the room and I said there's a wheel spinning with its angular velocity towards the back of the room, everyone should then know by the convention that it's spinning around like this. If it's pointing towards the ceiling, then it's spinning around like that. Other questions? So we have a wheel with a radius of 0.5 meters, spins with an initial angular velocity of positive 30 radians per second. Two clues that we're dealing with a velocity here, a vector is one. I actually use the word velocity here for angular velocity, and the plus sign here emphasizing the fact that there is a direction here. A 4 Newton force is applied to the tangent to the edge, at the edge. Let's just go ahead and make it a 4 Newton friction force, just so that it's obvious that it's trying to slow it down. It's trying to slow it down. I just thought of how a friction force could actually speed it up. How long before the wheel stops? So the visual, so if we go with our convention over there, positive is towards the back of the room. So I'm going to spin it this way, counterclockwise to you. And then a force is applied to the edge, slowing it down. The question is, how long does it take to stop? Let's look at all the pieces that we have. We've talked about torque already. I got my wheel here, and it is spinning counterclockwise, and I'm applying a friction force. It is sliding over, and it's not a static friction force. A static friction force probably would not slow it down. Here's an example of a static friction force, so let's see if I can do this without hurting myself. That's a static friction force right there. Because my hand was on it and there was no sliding whatsoever. My hand just started moving with it. And I did not hurt myself. All right, so let's see what we know here. We solve it exactly the same way we were doing problems in chapter 2, except we just changed the symbol. We have our angular displacement. We have initial velocity, angular velocity, final angular velocity, angular acceleration, and time. What do we know?
The initial angular velocity.
All right. And we know one other thing.
Would the final be 0?
Yes, it would. Positive 0 or negative 0. Whatever your mood is. Yeah, when I was taking pre-calculus, we did a proof that positive 0 equaled negative 0. And then taking I think it was the PSAT, and there was a question where, is positive 0 and negative 0 the same number, or are they just two numbers that are equal to each other? And depending on how you interpret that question, came up with two completely different answers.
What's PSAT?
You know what the SAT is?
Oh, okay.
It's the preliminary. Just another standardized test. All right, so we don't know anything else given this, but we do have a little bit of information here. What exactly does the force have to do with the rotation? Just do a simple explanation, then we'll get into the physics if need be. What's the force doing? Okay, so since we are causing a change in the angular velocity, what influence causes that?
Angular acceleration.
That would be the result of it.
Would it be the friction? Or
going for the physics, I guess that is a physics term. Friction is the force itself, but what is the force doing to cause angular acceleration? Just applying a force is not enough. I can apply a 4 Newton force to it and it not slow down. This goes back to what we did on Thursday.
Is it inertia?
Inertia says it's going to continue going at 30 radians per second unless we apply something to it. Okay. Does the name Jitu Kabuka ring a bell?
You said it last class, but I forgot.
Yeah. And what is it? Torque. Yeah. Yeah. The force applies a torque. That is the influence which causes a change in the angular velocity. In other words, that is the influence which causes angular acceleration. So from this, we can figure out the torque. Once we have the torque, we can figure out the angular acceleration. I guess I do need to give a little bit of detail here. I guess I need to give a mass. Oh, let's make it a 2 kilogram mass and assume spokes are massless. In other words, what I'm going for is all the mass is right there at the rim. We'll just simplify it that much. So if I'm applying a force at this spot right here, how do I find the actual torque? All right, so that would, but we need to be able to figure out torque some other way. We can calculate that. There's a formula for this. This is what we're trying to find out. So we don't know this in order to calculate torque. We need to find torque a separate way in order to find angular acceleration. What's the formula for torque? An individual torque. The one that Marisol gave, that's the total torque. Times what? Nope, I think you're misreading. It shouldn't be momentum, it should be moment.
Moment arm, yeah.
Yep.
Moment arm times force.
Times force, yeah. R cross F. Yeah, moment arm.
Moment arm.
It is unfortunate that the word moment looks like it's in momentum. Coincidence as best as I can tell. So the cross product tells us that we want perpendicular. So we have R. R is a vector from the axis of rotation to where the force is applied. So the magnitude of my torque would just be RF sine of theta. So that's 0.5 times 4, so 0.5 meters, times 4 newtons, times the sine of, what is the angle between them?
Between what?
Between R and F, between my moment arm and the force.
Since it's perpendicular, is it 90?
Yes, it is. Now it's perpendicular because when you put them tail to tail, that's a 90-degree angle right there. When you're trying to find the angle, it's tail to tail that's key, not head to tail. So it's still 90 degrees. And we end up with 2 what? Why do you get joules?
Newton meter.
You said,
Newton meter.
all right. So when we dealt with energy, a Newton meter was indeed a joule. However, this Newton meter is not. torque and work both give us units of Newton meters. It's just that when you were talking about torque, it is not joules. They really did not come up with a better system. It's just the way that it happens to work out, but not joules.
So the lever arm is pretty much the radius.
Yes,
Okay.
but specifically from the axis of rotation to where the force is applied. And so I've given problems in the past where I've had sort of a double, two discs stuck like that, and I have a string attached to one of them, and the force is applied to the outside. And so just recognize the torque from here is dealing with that radius, the torque from the string is dealing with that radius. And that's not a division design there, that's all. So, all right. Now the moment of inertia. What is the formula for the moment of inertia if I'm thinking about something like this, all the mass on the outside, spokes are massless. What's the formula for the moment of inertia?
It's the integral of R squared.
MR squared.
Yeah, let's, if you're gonna do the calculus part, that's fine, but on this case, we actually have a simpler formula already done. Precious?
MR squared.
MR squared. And so my moment of inertia, mr squared, with all the mass on the outside, all the mass is the same distance away from the axis. And so we end up with 2 times 0.5 squared, which is 0.5 units. Sorry?
kg meter squared.
Yes. Kilogram meter squared, that's 2 kilograms and 0.5 meters squared. So we now can find the angular acceleration using the formula that was spoken of earlier. So I have 2 is equal to 0.5 times alpha. Doing the fancy math, alpha is equal to 4 mathematically. Now obviously I've ignored units here. That's 2 Newton meters. That's 5.5 kilogram meters squared. Let's write that out so it can actually be a little bit more legible. Potentially darker. Torque is equal to I alpha. So I have 2 Newton meters is equal to 0.5 kilogram meters squared times alpha.
I have a question.
Yes.
So it says that RF sine theta is equal to the magnitude of torque, which is 2.
Right.
And then on top of that, you have the torque, which does not have the magnitude sign. Is that important?
What, up here?
Yeah.
Yes, the direction is of importance. I was gonna do that in a moment, but we can do it now if you wish.
Oh,
Let's go ahead and do direction. What is the direction of the torque? Probably makes sense to do it all at once.
R, go in that direction.
Okay. So if we think about R cross F, I have R going up, I want my fingers to point easily towards the second vector, so R cross F is in the back. Or in absence of anything else, if that's the only force acting on it, it would cause this thing to rotate in that direction, in a clockwise direction. If we assume our convention over there, our torque is negative 2 Newton meters. I guess I just have a positive there, so it is slowing it down, it's going in the opposite direction, so it has to be the opposite sign of that. So therefore, put the vector symbol in there, the -2, -4, and we're back to what are the units?
Would it just be radians over second squared?
It would be. And now we need to find time. So what formula do we use in order to find time?
So, the final equals
Final what?
final angular,
As in velocity?
yes,
Okay, final angular velocity.
equals the initial angular velocity plus the angular acceleration times time.
Yep. It's one of the cake formulas. It's one of the rotational cake formulas. You just take, instead of V, you have a W. Instead of A, you have alpha. Wow. Try that again. Instead of V, you have omega. I think I did say W, right?
Yeah.
Yeah, then strike that from the record. You have an omega. Instead of A, you have alpha. As soon as I said W, it would have been perfectly fine for one of you just to go, whoa, no. So now it's 30 is equal to 0, or doing it the other way, 0 is equal to 30 plus -4t. T is 7.5 seconds. Questions there before we change the problem slightly? Well, before we add to the problem. This messed up a student I had a couple years ago. English was not her first language, and whenever asked how long, she saw the word long and she immediately thought I was asking about distance instead of time. I hope that doesn't mess you up. If you ever see how long, and you're not quite sure of the context, just ask. So this was meant to be time. I now want to know through what angle, no, through how many revolutions? Will the wheel spin while stopping? This is 7.5 seconds. So what variable am I asking us to find? People are pointing. You're unsure what the letter is?
Delta theta?
Yes, okay. So what formula would we use?
The change in delta theta,
Or okay, delta theta.
oh yeah, equals omega, the initial, times time, plus 1/2 alpha t squared.
Yep, there we go, that one works. So that is equal to 30 times 7.5 plus 1/2 times -4 times 7.5 squared. Yeah, my gut said it was 112.5, but I didn't see where my mistake was, but you almost anywhere. So,
That's 112.5 also.
units?
Radians.
Radians, yeah. Now be careful, because that actually does not answer the question. We found delta theta, yes. That was key, we had to do that. That would get you almost all the points, there's just that little bit at the end, because the question says, through how many revolutions? If I just said, what's the angular displacement, or through what angle does it go, then yes, we're done. But the question is how many revolutions, so we need to be able to convert this into revolutions. And that is simple enough. It's conversion. I have 112.5 radians. Well, how many revolutions in a radian, or radians in a revolution?
30 per second. Isn't it 30 radians per second?
Oh, that's only initial speed. This is conversion. In general, how many radians in a revolution? 2 pi. Don't forget the pi. And so 112.5 divided by 2 pi is,
17.9.
what is it?
17.9 revolutions.
And now we can answer the question. Questions to hear? All right, let's talk about center of mass, sort of new topic-ish. Which I'll sometimes abbreviate as CM, please don't confuse it with centimeters. In other words, if I have some shape right here, And in order to figure out where the center of mass is, well, I've got some sort of coordinate system, and there's some vector to the center of mass. In essence, we're trying to find an average here. Well, we can start with the calculus version of it. If I'm trying to find the average value of a position, well, whenever you're finding average, I'm looking at distribution of mass here. So this would be R dm, the integral of dm. Just for convenience, I'm going to drop that vector notation. You could do it in the x direction and in the y direction to get your x and y coordinates. The denominator here is just the mass. You're integrating over dm, so that would just be m from whatever initial to final bit is. And so this just becomes the integral of r dm over whatever the total mass is. Now the calculus version is just, again, it's just the average position with respect to mass. We can take something a little bit simpler. I have a rod here that is 2 meters long with a mass of, we'll make it 2 kilograms. Let's do a different number, 3 kilograms. I have a, let's make this 0.5 meters by 1 meter. And its mass, well, this mass of rod and mass of box is 2.5 kilograms. Remember that integration is just a whole bunch of adding up. It's just an infinite sum. But if I already have something with two objects which are uniformly with uniform distribution, well, I pretty much know where the center of mass is. And the center of mass is going to be in the middle. But if I want to define where the center of mass is, I need a coordinate system. Where's 0?